and record. Okay, well now, you should be able to move things around. We started a little bit late, so let's 136. Guess we are to 220, so maybe let's go to 2. Then you can bring, maybe before 2, 157, so that this is.
Okay, sure. Okay, so we are team 3 and we will be talking about how to do autonomous off-road driving with a controller. So let's start with some inspirations. So before we talk about off-road driving, let's talk about on-road driving first. So on-road driving is relatively predictable. Usually what you do is you make some assumptions about the system or the states being linear, and you construct some linearized models with it. For example, in the seminal book, The Fundamentals of Vehicle Dynamics, what they did is they assumes a model that is 2 degrees of freedom, and it's basically functions like a bicycle. So you have X and Y translations. And also in this work in 1995, you have linearized PID controller, which after implementing and running on the robots, you can see this is the graph showing the error. It might be hard to see the statistics, but usually like they have like mean error in meters that is less than 0.1 meters. So that is pretty good. And in 1999, there's also another work that adds a sensor at the tail of the vehicle to supplement the sensor at the front of the vehicle. And using like these 2 sensors, you can get a more accurate measurement. And you can also measure the angular displacement aside from the translation. And these are the 2 graphs showing the angle and displacement of this work. And as you can see, the lateral displacement relatively like centers around 0 meter, which is very accurate. And for the steering angle, it's less than 1 degree most of the time. So off-road driving is different because you're not driving on the public road, you're driving on nature. So you have these unpredictable nonlinear elements that impacts the accuracy and orientation of your car. So that's why linear control method does not work because of these linear, nonlinear dynamics. For example, the gravels on the road, the sharp curves, and also the mud puddles on the way. So you don't have smooth road surfaces, and there's no global stability because of how the road is constructed. For example, one side of your car might be tilted upwards, so that your tracking accuracy or the sensor measurement might be very inaccurate from the reality. So these are some work that represent the failed attempts at autonomous off-road driving. So in this work at 2000, they used a crossoid-based model predictor controller. What crossoid means is it's basically like a spiral shape, like this one shown. So that instead of having a sharp turn, you change the orientation of the car slowly over time across over a longer distance, so that your driving is more safe and controllable. They also used a speed indexed obstacle clearance, which simply means your distance to the obstacle is proportional to your speed. So as the car's speed increases, the car keeps more distance away from the obstacles. And in this case, the obstacle is anything that is not on the car. And it is able to drive off-road at speeds up to 22 miles per hour or 35 kilometers per hour. And the tracking error, however, this method doesn't really work because the tracking error and clearance distance increases with speed. And usually when the car drives more than 25 miles per hour, the tracking error just increases exponentially. Another attempt, which is a more popular attempt at 1998 and other years as well, is that they broke up the process into layers. So at the top layer, you have high-level planning where you select the destination and major waypoints. In the middle layer, you do some sort of path planning to avoid all the obstacles, but you don't move the car yet. And in the bottom layer, you use the PID controller to basically like point the front wheels toward the goal point ahead of the trajectory and minimize the difference. And I think for the bottom layer, we covered that during the class, so I won't go into the details. However, this method doesn't really work because of its poor performance in tight curves. Because when the curves are very tight, so not like the curves shown in the picture, when it's like almost 90-degree curves, the error will be very huge because they don't have time to react to the change in orientation.
The idea with the first one was because they have to go slowly.
Yeah, it has to go slow. I guess like the major issue with the first one is because when the speed, so since the speed increases proportionate to the obstacle clearance distance, so when the speed is very large, the clearance distance has to be very large, but that is not practical in every situation. Yeah. So this is what our paper did. I will provide a very brief method overview, and then Ashley will go into details on the equations and stuff. So the first contribution is that it considers the orientation of the front wheels with respect to the desired trajectory instead of the entire car. So the benefit of this is you have a more collocated control of the system. Collocated control basically means that the actuator and the sensor is very close to each other so that you have more immediate feedback and control. And aside from that, it uses two processes. The first process is it has a nonlinear control law to control the orientation of the car. And it just controls the tire and the steering wheel. And they also have a switching PI controller to control the speed of the car. In this case, the brake and throttle. Yeah. Any questions? Okay. I guess then Ashley will talk about the details of the.
Okay, so this is the lateral control law, which is just for the steering. There is no moving forward or backward here. This is solely the steering. So the bottom two equations are just saying that if the steering angle that we want is exceeding the maximum that the wheel can actually turn, then we want to just steer the max and not go overboard. The top equation, so we have the arctangent of the error and over the velocity, which down here, if you think about that angle, it's this little angle that's between the velocity and this red line. And then essentially you're adding feet to it, or side. And so that's this little angle. And so you know that this whole thing is actually the delta. So another way that we can think about this is that oh no, there's a next slide. So E is the error. So E is the error and V of t is the velocity. So another way we can think of this equation is that E over V of t is essentially how fast you are approaching the trajectory line. And then E is on top because if you have a lot of error, then you want to steer harder in the direction of the trajectory because you want to get there faster. And then V of t is on the bottom because if you don't want to steer too hard if you're going too fast or your car may slip. So that's actually the top equation there. So that was the main equation. Now they've added some dampening to make sure that it doesn't get messed up by various real world conditions. So we know that cars can only steer so fast before they they just have only a maximum speed that they can turn. So they added a term which is the difference between how fast the car is actually turning and the rate at which we want the trajectory is turning. So it's like the car not is turn, it is the angle of the car versus the angle of the trajectory. So if the car is like pointed toward the trajectory or away from it. And then the other equation is the steering. So that is the steering wheel was controlled by a servo, and that servo has a limit to how fast it can actually turn. So we take the measurement of the basically measuring time for like how fast it's actually steering, and we take that into account.
So, just to understand this intuitively, does this mean you like oversteer so that you make up for lag, or like,
No,
what is, so basically you're saying servos can only turn so fast, does that mean you increase the control so that when you lag, you get to where you want to get to, or what is?
I believe yes, because essentially the car is planning so that like if you don't add this, then the car will say like we instantly want to turn at this angle, but in reality you can't instantly turn at that angle. That the servo needs time to move there. So you're just adding that.
And does that mean I can imagine so that it like transfers, or does it mean that, hey, what is it, like, can you help us understand intuitively? Like basically, there's the instantaneous assumption, and this thing is going to make up for it, but how does it make up for it? Does it increase the magnitude, or?
So in the end, what we're gonna do is add this term. So just onto like the previous equation that I showed you. So based on that, I think what it's doing is just adding. This is a cave-in. When you look at the previous equation.
I mean, like adds delta
like-
plus those two terms. Your
Yeah.
explanation makes sense. I'm just trying to understand, like, is it like oversteering to make up for the lag, or what?
No, I think
Anyone else?
it might be oversteering.
So I think it's basically like not like exactly like the lag where the system sends the controller, but rather just that how much you can turn the servo.
Mhm.
It's
Okay.
that kind of.
Yeah.
I see.
I was just gonna say, I think because each individual point, like if you are turning to 10, you don't want to say that you're at 10. You want to say that you're at 2 at this point, and then the next point, okay, now I'm at 4, now I'm at 8, all the way up to 10.
Right, but then it's like interesting that you like added to delta, so it's almost like you're increasing delta to make up for it. It's not that you're changing your measurement is your measurement, but you're changing delta. So it sounds to me like you're changing delta by scaling for the amount of like lag, whether that's servo lag or whatever.
Yeah, I think it's because like if you are in the process of turning, then you're not going to steer as much as if you had turned all the way instantly. So you need to turn a little more to make up for the fact that you have this like change in steering. Yeah. So this is to make up for the fact that the rear tires on a car that is steering create a sideways force. As you can see when the car is drifting, that becomes especially evident there. So this equation, I'm not going to go into it too deeply, but essentially it's an equation to calculate the sideways force based on the tire stiffness and also the car length. So this is going to also be added into be accounted for and added to the steering equation. So this is combining this is the sideways force. So this is adding everything together, and this was basically how they calculated the steering angle. So for moving, for how much they move forward or backward, they used a PI controller. And in this case, V is how much the car is actually going versus the commanded speed that the algorithm wants it to go. So for the P term, we're just taking the difference of between our expectation and reality. And then for the integral term, we're doing the same thing, except we're recursively adding itself onto there. So, if there was an error in a previous time step, that error is accumulated on, as you're adding onto the integral term at each time step.
Into I on the right,
E int of I plus one.
like both sides of E into I.
Yeah, that's because you are adding, it's an integral term, so you want to accumulate the error at each time step. So,
But it's like,
It's kind of like CS terms. It's like adding on the original.
Oh,
But
sure.
I
Oh,
feel
okay,
it's
I
not.
see.
yeah, yeah,
Yeah.
Oh, I see.
you have
Yeah.
I plus one plus equals that, yeah. So they used just a brake and throttle. They didn't use much else other than controlling a brake and a throttle, and that's all they did for how much they move forward or slowed down.
All right.
Mhm.
So before we get to measurements, before we get to experimental results, we should talk about measurements. So in this paper, we measure the cross-track error, which is measurement of how far a vehicle deviates from the intended path. So right here, this is the intended path, and this is the actual path. So the magnitude will be represented how far away it is from the path. And then the sign, like plus or minus, will determine which side of it it's deviates from. Next up, root mean square error. So it's a measurement of to quantify the average magnitude of error from the desired path. And this is the equation. Obviously, the lower it is, the better it is. Next up is experimental results. So they did 3 experiments. The first experiment they did off-road. So they did it in the Arizona desert, and the terrain of it is it's a loop of gravel with a lot of erosion, and there's a lot of curvy, windy roads, and you have to go like up and down, uphill. And then if you look like up there, that's the whole path, and then right here, this is the altitude. So the highest altitude that they go is 30. And you also measure the cross-track errors in this graph from 0 to 10. As you can see, cross-track error is from negative 0.5 to 0.5 meters, which is pretty low. Next up is, they also did it in the, hopefully I don't butcher the name, Mojave Desert, which is part of the DERPA Grand Challenge 2004, the same course. So DERPA is the Defense Advanced Research something agency, where projects agency, where the government funds like this racetrack for teams to, like, develop autonomous vehicles for like military use. So
The last section, was that, is that 0.3 centimeters? cross-track error?
wait, which one? Oh.
I think he means the average cross-track.
Like.
Oh, the skippers? Oh.
0.003 meters.
Yeah,
0.3, that's 3 millimeters of cross-track.
yeah, that's how they presented in the paper.
See, it's kind of wide.
Oh yeah, go on to, yeah, so
Like the
Yeah.
car is like several feet long.
yeah, they said it's way less than the width of the wheels.
Huh.
All right, yeah, I clicked here. So
How do you even measure that?
yeah,
I'm pretty sure that.
it didn't explain how the measurement was worked, so I'll just take at face value.
I don't believe that, that's.
Yeah.
like crazy, isn't it?
It's very minimal.
Yeah, I think, it is 0.003, I think.
We did say that.
Yeah.
Yeah.
It did say that.
Oh yeah, so CT is 0.003 meters, the standard deviation is 0.02 meters. And then they were able to soar about 25 miles per hour on those very curvy roads.
Maybe it's like really bad extreme, but it all
Hmm.
happens that very little.
Yeah, next up is, so the DERPA Grand Challenge 2004 map. Here, there's a lot of, they tested it on a rainy day or like a rainy day, yeah. So there's a lot of puddles that are 0.1 meters higher in depth. Because of this, the puddles will cause sliding. And this model is able to compensate for sliding via the controller with only 0.2 to 0.5 meters of cross-track error. And they're able to do that at 15 miles per hour. And also a limitation that Alex will mention later is how the angular rate is not measured to the controller. But despite that, this model is able to swerve around obstacles at 35 miles per hour while counter strafing with a maximum CTE of 1.5. Oh, sorry, wrong one. Next up is the second experiment, endurance. So right here, they did it in the Volkswagen Arizona Proving Ground, where they looped around the course for 88 repetitions. And the course is a open loop, closed loop that spans 2.3 miles long. So based on that, this is the endurance test. And this is the count of how many cross-track errors based off of those 88 repetitions. As you can see, it as a unimodal distribution towards like 0, which is hard to believe, but you know. Next up is the final experiment, which they actually took it onto the Surfer Ground Challenge of 2005. Previously, they did 2004, which is already passed. So, but 2005 is like the entry into the competition. So here, there's 23 different contestants from different schools with a $2 million prize pool to the winner. So they implemented on the Volkswagen Touareg, which is also known as the Stanley, which is the Stanford Racing Team's car. Sorry. So, am I missing? Sorry. Yeah, this is the Stanley.
So did they change the model across the stuff? Or is it just changing the wheelbase length? Like what changes?
I think they just implemented the model onto the car.
No, what
Oh.
is like across the cars,
Mhm.
the controller, what you, like, do they tune the gain separately or like? Did they say anything about that? Or is it literally the same?
I'm not sure if they
I think
mentioned
they
it.
just,
Yeah,
I
they
think
didn't.
they mentioned, but they probably just did like hyperparameter tuning.
They had variables that were A and B, which were the wheelbase. So they probably took that into account for each car.
Next up, this is the result. Oh wait, before the actual like event, they had to qualify for it. So first they have to attend the qualification event, which is held in the Ontario Motor Speedway, and it has obstacles that simulate the actual terrains. So real quick, I can show you the map. This is the simulated map for the qualification. So here, the results, CTA is very low, 0.01 on average. And then the root mean squared error and the standard deviation is 0.05. And fun fact is that this is the only car that did not hit any obstacles in this whole qualification event. And yes, and I'll share the trajectory of the whole racetrack.
We all have like one more minute.
Okay.
Let's,
We can,
You can skip it. You
Yeah,
can skip the video.
yeah, especially during the challenge, they got first place. They also had some big errors due to like, they didn't check, but they say it was due to incorrect calibration on the steering wheels. And this is the video.
We'll see now.
We can skip that. And they placed number 1.
alright, so quickly go over the limitations. Okay, sorry.
Sorry.
Quickly go over the limitations. The first thing, they have a lot of assumptions in the kinematic model. The first thing they said like the model has negligible inertia, which is fine when they're driving at lower speed. I think in the competition they did around 19.1 miles per hour on average, but they did mention that when the car is driving at a higher speed, this the inertia might not be negligible, which would cause deviations in the kinematics model. Tire forces, they simplified a lot of force calculation, didn't really do a lot of for example friction that kind of force during their calculation, and that's also part of the reason they did not really take account of weather conditions. For example, in the first test they did, when there were puddles, the cross-track error is significantly higher because they didn't really take account of like how much sliding there were. In terms of the control, first thing, the control output rate is fixed and is like slightly lower than probably what we expect now.
And the throttle action was also simplified. It's also simplified. They said in the paper that it was an acceptable simplification, although they didn't really talk about why it's acceptable or what's the experiment they did with that. But they did say that it was simplified. And also, so they did a negative damping based on negative feedback on yaw rate, which is sort of like hyperparameter they keep tuning, which could be different when the racetrack is different. They fine tune to this specific racetrack. And then they're also like the change of angular rate of trajectory did not get feed forward to the controller, which means they had the significantly higher cross-track error when they're entering a curve and then when they're exiting a curve, because at these points, the angular rate changed significantly and they didn't really look forward. And also that there could be system delay, there could be they didn't take account of the steering delay of I can't steer the servo like to like a certain degree like immediately, but they didn't really take account of the system delay. Like I would send the for signal processing etc. Which means for possible future work. I believe this model, the Stanley model, have been used a lot for future works, and they adapted like multiple changes. Like they have multiple changes based on different adaptations, and based on this model. And so first thing they could do is that just update the higher kinematic model to consider more terrain types and weather condition. For example, slippery roads, or like so basically friction, all that kind of scenario. And also they could probably use enhance the state estimation model. I believe we could probably use LiDAR or some sort of sensor model of some sort. Definitely use a higher output control rate, higher than 20 Hertz, which will definitely reduce the amount of error during each time step. Feed the curvature pass forward to reduce the impact system delay. I believe there was a paper in 2023 which they did this, and they reduced the error from 0.11 meters to 0.03 meters, I believe. And then modify control law to be more robust under higher speed. During the racetrack, they were traveling at 19.1 miles per hour. They could have it higher. They did say that the control law will be less accurate and will be less stable. And also, one of the other main drawback is that the controller parameter were all fine-tuned by themselves, hand-tuned by themselves for specific type of roads. In this case, the DARPA Grand Challenge had gravel roads, the specific obstacles, so they fine-tuned all the parameters according to that. But however, in a real scenario, if you want to use a autonomous driving car in an off-road scenario, we might need to adapt to all kinds of scenarios, which means we probably would want to either have some model to fine-tune it or just use an adaptive controller so that it will adjust based on the terrain. So.
Did everyone get a chance to go?
Because follow was like
I think just to give the other group a chance
Yeah.
to go. Yeah, so let's thank group 2-3.
Good job.
Guys wanna send it to me or plug yours in?
Yeah, thank you. That's great.
Yeah. We also have a DAOE slide at the end.
Ah, very nice.
Yeah.
That's Stanley in 2024.
I'm generating similar images, which is
Really?
interesting.
Ah, that's curious. You send me something already?
I almost completed this for.
Okay. Got it. Wait. There you go.
Go ahead.
Okay, hi everyone. Today we're going to be talking about sampling-based model predictive control, leveraging parallelizable physics simulations. Okay, so just some background info. So robots are becoming more integrated into our daily life, which means that it's more important for them to be able to interact with the environment. But at the same time, it's also becoming more challenging because robotic platforms are getting very complicated. And there are existing solutions, but a lot of them are very specialized, which means that it's like hard to transfer to like various robots or like various scenarios. Okay, so the paper proposes this idea of using a training-free model-based framework for real-time control of these complex systems. So it talks about MPPI, which we talk a little bit about in class, that we're going to talk about more in detail later. But MPPI still requires some substantial modeling. So the solution that the paper proposes is to use something called Isaac Gym, which is sort of like a physics simulator, and use this as a model for MPPI. And yeah, we're going to talk more about this in the next few slides. And yeah, this allows for the creation of a more robust framework, and this can now solve the issue of being able to generalize to like different types of tasks and robots.
Okay, so for the method, it uses MPPI as it mentioned earlier. And we covered this in lecture, but I'm just going to go over it and compare and contrast the different tricks they use. So here is the standard like formulas, right? You have this state xt plus 1, and you have like a f function, which is a nonlinear state transition function. And it essentially shows how the state x evolves over time t. With the control input v sub t, where v sub t is like sampled from this noisy version of u sub t, which is just a control input, and then you have a covariance. And then the next,
You told us what U, T, and covariance are yet? Do they just like appear magically?
u sub t is a control input, and then covariance is.
Yeah, but like as in how do you choose to like? You're
Oh,
solving-
I'll talk about, so, I mean, initially you choose it, but then you keep on applying this like optimal control inputs. Yeah. So the next step is like, we want to sample, right? So we have our state and we're just gonna sample, and these state trajectories, we denote Q sub K. Wait, before that, we sample K noisy input sequences V sub K that are applied to the system to simulate K state trajectories. And these state trajectories we denote Q sub K, where K is inside 1 to K over a time horizon T. So we're just trying to say like, given a state, we want to plan the next T time steps and see where that state trajectory Q sub K goes. And then earlier we mentioned, and this paper attempts to use a training-free model-based framework where the user really only has to specify a cost function. This is that particular cost function we're going to use, and we're going to call that S of K. And then we apply this idea called importance sampling, in which we like assign weights to each of these trajectories, since like not all of them are equal or important. And I'll dive into the weight formula in the next slide. So let's break this down. We have rho here, which is like the minimum sampled cost. And we subtract by the total state cost S of K, but no, we subtract rho by the total state cost S of K because we essentially just want positive numbers. Another way to view this is like, you want the lowest cost scenario to have weight 1 because like exponent of 0 is just 1, which is like the highest possible weight any scenario can have before it's normalized. And then like you have this like negative term here, right? Like what is that? It's essentially to flip the relationship of the exponential. So like as the cost gets large, the term becomes more negative, and then that makes the the weight smaller and closer to 0. And then we want high cost to have low weights and low cost to have high weights. So yeah. And then we have this beta term, right? The beta term essentially controls like the sensitivity of the weights to the cost. So like if beta is large, then the weights change more slowly with the cost. And we can view this almost like an exploratory and exploitatory situation, where like exploratory would be like if beta was small, and exploitation is like if beta was large. And it's like a parameter you want to tune. I think they do some metric of tuning in the paper. I forgot.
Exploration is beta is large. exploit it.
Exploration if beta is large.
Exploration, because beta is large.
Yeah, oh yeah, yeah. You could also view it like the Gaussian, right? It's wider and then narrower. Okay, yeah, that makes more sense. So it's like a parameter you want to tune for beta, and then you can also view it as like earlier the Gaussian, and then essentially we exponentiate all this, normalize it, and then so it sums up to 1. And then now we compute U star, which is like the optimal control input sequence by summing over the weighted input sequences. Repeat by putting U star into our sampling distribution as U sub t, as you mentioned earlier, like where does that U sub t come from? And in lecture, this is the same process as like we want to narrow down the path that we're sampling from. Yeah, we want to narrow down where we're sampling from. Okay, so now it's time to get to what they did, right? And there's pseudocode on the side. And first thing they do is initialize a sequence of control inputs, U init, with length horizon T. And it's essentially, like I said earlier, you want to plan for the number of steps in the future. The next step, which is the epsilon of K, is you want to generate K different sequences of random noise to explore. And we use this algorithm called Halton splines. It's another paper. And essentially what Halton splines does is it allows us to like sample trajectories that are smoother. So in like this ugly graph that I drew, you see that like you have the same exact dots, but like your trajectories are smoother. Just abstract that away. And then they use Isaac Gym to simulate the case simulations that can give you different possible futures called rollouts. For each rollout, we are going to calculate a cost using our defined cost function and then apply our weights and repeat until this task is done, right? So pretty much the same as the old method, except I think at the end, they time shift their U star backward 1 step because time has already moved on 1 step since you started this process. And they referred to it as a warm start. That didn't really make sense to me. Okay, and I also wanted to mention that they have a slightly different total state cost function in which they have this like gamma discounting factor. And what it's saying is like a reward received now is better than a reward or worth more to me than a reward received later. And then I think the key takeaway here is that we are not explicitly defining a nonlinear function f. Instead, Isaac Gym computes the next state for us. And this is done by like resetting the singularity to the observed values, then adding noise to simulate the state trajectories in Isaac Gym. Also, things I wanted to mention is Isaac Gym tackles the problem of the computationally expensive aspect of MPPI by just, paralyzing GPUs. Then finally, I didn't really mention much of this, but Isaac Gym also has these built-in features that check for collision checking and model uncertainty.
Okay, cool. So now that we've heard about what new techniques the researchers are using with combining MPPI and Isaac Gym, let's figure out how well their technique worked against some of their benchmarks. So they basically test their method's effectiveness under 3 categories of experiments. The first category is motion planning and collision avoidance, which is like how well does the robot using this method plan their path to their goal and avoid collisions with obstacles. The second category is whole body control of high degree of freedom systems. So basically, how well does a robot with high degrees of freedom account for incorrect error? And then the third category that they are experimenting was non-prehensile manipulation, which is a fancy way of saying how well does a robot with their method manipulate objects without holding them. In their experiment, the robot primarily moves objects through pushing them. Cool. So part A, this again is the motion planning and collision avoidance. How they tested the robot their method was that they had 2 different types of robots. On the left, you have a robot that kind of can move in 3 dimensions on the ground. And then on the right, you have a robot that is a robotic arm. And then the left has 3 degrees of freedom and the right robot has 7 degrees of freedom. And so they're basically going to test how well do the robots using their method get into that green goal location. And they'll be testing their performance against two benchmarks, a robot using their method called optimization fabrics that was researched by another researcher, and a robot following Proforce's MPC. Yeah, okay. So basically what they found was that with their method of using MPPI and IsaacGym, they had comparable path length clearance, which is like the distance that their paths that they calculated were from the obstacle. So they want to minimize that against their benchmarks, but they found that their method has a faster convergence rate. So their robots were able to get to the goal location faster. That's the part A experiment. For part B, part B was about how well do their robots account for error, especially robots with the high degrees of freedom. Their experiment was simulating this robot arm that can move in 3 directions, how well it can grab the object on the table and move it to the goal location. They measured the time it takes for the robot to get the object to the goal location, but they didn't really compare it against any benchmarks. But they did say that with their method of control, they were able to, I think the quote was, have fluid motion from start to stop. So according to them, their control system creates fluid motion. So that's good. And then part C, there's a lot on this slide, but most of their experiment was in figure 6. So they have a robot arm that pushes an object to, again, a goal location. And now in this experiment, their benchmarks were 2 different MPPI methods that didn't use IsaacGym. So they used trained models instead of a physics simulator. And they had 2 different sets of experiments for figure 6. There was one where they pushed one small object to the goal location, and then another experiment where you had 5 different objects of different sizes, but they were all much larger, pushing those into the goal location. And then they found that their method outperformed the other 2 MPPI methods that use trained models because they had less overall cost by the end of their robot solving these problems, and they solved them faster. One caveat of the results is sometimes the results from the data that they were comparing their model against were incomplete, so they kind of guessed on those ones. So if you ever see a squiggly line, they're guessing. So like, especially in table 3, like they kind of were guessing for all of the time. So I don't know how true those results were, but they felt that theirs was better. And then figure 8 and figure 9, they just wanted to show how their model could extend to other types of robots besides that robot arm. So in figure 8, they have a robot that's pushing around object, and it's a robot like that drives on the ground. And then figure 9, they have another robot that drives on the ground but can only move its, I think, front 2 wheels. And it's moving a rectangular object. Okay. I don't know if we have time to finish, but in terms of the real world experiments, they took the experiments from C and then they applied it to real life, and they found that the robots could solve the problems that were set for them in real life, even when they messed around with the robots. There's a cool video, but yeah.
Okay, yeah, this paper is very recent, so like 2 months ago, so there are a lot of like previous related works. Let's do this.
Okay, let's get to some hating. So some of the things we didn't like about this is a lot of the comparisons we found trouble with, like their method took significantly longer to compute their solutions than other methods. I could solve the problem too if you give me a few years to do it. So of course they performed better. For part P, there was no a comparison at all. So you don't have any context to whether this is a good or bad solution, really, just that it is a solution. This graph in particular, I don't know what's happening here. If one of you knows, please tell me. And then the real world experiments, they only did non-prehensile. One of their main points was that it was generalizable to different systems. So I would have liked to see them try a prehensile task where they grab something. I think we're out of time. And also IsaacGym, their main point is they use IsaacGym, but they don't discuss any setup you have to do. You have to model the situation in IsaacGym, probably set something up to connect it to the robot. There's no discussion of that at all. I would like to see.
Right. Please, feel free to ask the questions. Right, you all are doing great presentations. But we'll have lecture on planning on Friday. Yeah.